Okay, we are back with the next speaker of this morning session, who is Carlos Gerardo Ciepielewski of the Universidad Nacional Autónoma de Mexico, and he will speak about on superdeterministic rejections of settings independence. Please, Carlos, go on.
Thank you, Federico, and thank you to all the organizers of this conference on quantum foundations. I'm very grateful to be here and to be able to share with you work that I find particularly interesting. This work was made with collaboration with Elias Ocon and Daniel Sudarsky, who are also in the call. Perhaps even in the questions, they can offer their insights. Okay. And this work is going to be published next year in the British Journal for the Philosophy of Science. Okay. So, okay, as a way of introduction, let me say a little bit about the motivation of this work. Okay. Because of the existence of Bell's theorem, and the fact that we have performed many times the relevant experiments related to such theorem, it seems that there are some non-local features in the universe, and we will see the details in a minute. But as an introduction, let me just state that if one wants to avoid this conclusion, it seems that possibly the only way to do so is to deny one of the assumptions in the theorem called settings independence. It might be that there are other assumptions in the theorem, but I would say that in most cases, I do not see any way of denying the other type of assumptions, or in general, I do not see other important assumptions that appear in the theorem. Okay. Then the work of non-locality becomes the work of seeing what reasons do we have in favor of settings independence, and what reasons do we have to believe in some of the ways of denying such an assumption. And in working on this evaluation of arguments, we stumbled upon a very interesting model that is going to be the subject of today's talk. Okay, so this is the structure of what we're going to do today. We're going to do a quick overview of Bell's theorem. Then we will move to discuss the assumption of settings independence. We will pay special attention to what reasons do we have to believe that something like settings independence is true, and what kind of reasons or what kind of models might be able to still say that such an assumption is incorrect. Finally, we are going to introduce the local pilot wave, this model that I think is really interesting. Okay, so let's start with Bell's theorem and a very quick overview. I think that most of the people in this call and in this conference are familiar with the theorem, but it will be a good exercise to go into the overall structure of the theorem and what it states. So we have a typical Bell-type experiment where we prepare an ensemble of two particles, and we send them to distant locations. In one location, we have Alice's lab, and in the other, we have Bob's lab. The capital A and capital B stand for the results of the experiments that each one performs. The results only can be up and down. Alice and Bob are measuring the spin of the system that is sent towards them. Of course, I don't know if I mentioned this, but the ensemble is of systems that we would describe as singlets in quantum mechanics. Lowercase a and lowercase b stand for the settings that Alice and Bob use. For example, the angle by which they put the Stengerlach or another measuring device they are using. And lambda is going to be a complete description of the system that Alice and Bob are measuring. So we're interested in this experimental setup. And Bell's theorem assumes two things regarding this general setup. The first thing is called local causality. And the idea of local causality is that suppose we have two distant regions, okay? And suppose that we have a complete specification of whatever is happening in a slide of the past hyperforce surface of a region of this first region, where something happens, some chi, a Bibel chi occurs, some event occurs. And the idea of local causality is that if I have information regarding sigma, and this information is complete, then whatever is happening outside in that other distant region must be irrelevant. Okay. In other words, the probability of whatever is happening in the first region must be independent of whatever happens in another region once I have conditionalized on sigma. Okay, in the theorem, this assumption takes the form of factorizability. I'm just going to assume that local causality implies factorizability for the purposes of this talk. So the idea is that the probability of Alice and Bob, once we have the measuring settings and the state of lambda, it goes like this. We can factorize the probabilities. Okay. The other assumption, and let me just state it, we will come back to it in a later moment. The assumption is that the distribution over this complete specification of the system of that Alice and Bob are going to measure is independent of the settings that Alice and Bob use to measure their respective particles. Okay, so Bell's theorem says that if one assumes factorizability and assumes settings independence, then the expectation value for the product of the results of Alice and Bob, which is this, is going to obey this inequality. This is a particular inequality that can be derived. There are many others that can be derived. The interesting thing, so far, Bell's theorem just is a derivation of this type of inequalities, but it becomes interesting when one notices that according to quantum mechanics, this combination of expectation values should be equal to 2 times the square root of 2 and not less or equal than 2. And we have performed the relevant experiments, and we always find that quantum mechanics seems to be right. So the conclusion seems to be that first, that no local theory can reproduce the predictions of quantum mechanics, and because of the experiments, that it seems that the world has some non-local features. Okay, that is the overview of Bell's theorem. Now we go in, to describe this assumption of settings independence and why it would be why we would consider it a reasonable assumption. Okay, so as I said, the assumption is very simple to state. It says that the distribution of the lambdas is going to be independent of the settings that Alice and Bob select. Something that I forgot to mention is that in the experimental setup we are imagining, we want to be as general as we can. So the idea would be that each time we prepare a system in a singlet, we are not going to assume that there is a unique complete description that is appropriate for that situation. At much, we are assuming that each time we prepare a system in a singlet, we have a distribution over the states of lambda. Okay, and then settings independence is the idea that this distribution of the whatever is really happening is independent of how Alice and Bob measure your system. 2 comments regarding some confusions that can that have arisen regarding this assumption. The first one is that this assumption has nothing to do with the free will of either Alice or Bob. The there is a long tradition of people being confused because of this, and there is even theorems regarding the free will of the particles involved. That seems to be a confusion. It's easy to see that it is a confusion when one realizes that this is just an assumption regarding the statistical character of the distribution of lambda. Another confusion has to do with how to understand the lambda that appears in this at this moment. And the thing is that lambda at this point must be understood as the complete description of the singlet of the system that we have prepared and that we call the singlet. Okay, this is before I mentioned when I was talking about the assumption of local causality that there is this complete specification in the past of a region. Okay, and some people think that lambda should be understood as this complete specification of the hypersurface in the past of a region. But in the theorem, lambda is not that. Lambda is just the complete specification of the system that Alice and Bob are measuring. Okay. Okay. So why would someone believe that an assumption like settings independence is reasonable? The answer is that we have performed the relevant experiments, and we have used a lot of methods to randomize how we choose either A and B. Okay, so we have used random number generators. We have used the digits of pi. We have used information coming from distant quasars. We have used even stranger things like the binary strings that can be extracted from information of popular movies and TV shows. For example, we have used information coming from the movies of Star Trek and Monty Python and the Holy Grail, and we have used that strings of binary digits to select the settings that Alice and Bob are using. And finally, we have even used inputs from a lot of people to perform these experiments. Why is this relevant? Well, the idea is that by choosing the settings randomly, we are in effect erasing any kind of correlations that we might expect that are present between the settings that we are using and the state of lambda. Okay. In the absence of some reason to believe that the correlation must be preserved, we think that these kind of processes ensure us that the settings are being chosen randomly. I hope that that is the main reason why we think that something like settings independence is a good idea. And as it might be obvious to some of you, it might not be obvious to some of you, but an assumption like settings independence is present each time we perform an experiment, in the sense that we assume that how we are measuring something must be independent of the system we're measuring. Let me be precise. We need to assume that it is possible to make those measurements or in a way that is independent of the system we are trying to measure. Okay. Okay. Let's continue. Okay. Still, there are two possible ways of denying settings independence. The first one is to assume a retrocausal model and to assume that it is the selection of the settings by Alice and Bob that causes changes in the lambdas that we have prepared. So the idea would be something like what is depicted in this diagram. The idea would be that we prepare the singlet state and it moves towards Alice's lab, for example. And when Alice decides or uses some device to select the setting A, that information travels backwards in time and then reaches Bob. This would be a way to deny settings independence. We are not going to talk about this possibility in here. We're going to talk about the second possibility of denying settings independence, which has the name of superdeterminism. And the idea would be that there is a common cause between all the elements in the experiment between the state of lambda that we are preparing and whatever is happening in the locations of Alice's lab and Bob's lab. Notice that because we have performed with these experiments using information coming from distant quasars, the common cause must be really, really back in time, okay? And it must be a really particular common cause, because it is somehow preserving the correlations between the settings and the state of lambda, even though we have used a lot of different things to try to randomize how we select A and B. So it would be something like akin to having a system that undergoes physical mixing, but preserves a particular correlation, even though there is a lot of intricate and ever-present different physical processes that we would think would erase any type of correlation. Okay, so these two possibilities seem to most people far-fetched. In particular, superdeterminism looks really bad, at least because of three reasons. It seems that a theory that a superdeterministic theory would be too complicated. Why? Because it would somehow be able to correlate these ways in which we randomize the settings of Alice and Bob with the state of lambda, and that seems too cumbersome. Second, it seems that doing this kind of move where we are saying that the correlations will be explained by postulating that there is a common past is like abandoning the project of finding an explanation of whatever is happening. Suppose we have a correlation between two variables. It is always possible to say that the correlation was there because the initial conditions of the system we're interested in were such and such. It seems that we are not giving an explanation. We're just assuming something about the initial conditions of the system. Lastly, it seems that such a position would jeopardize all experimental science. As I said, an assumption like settings independence is present in all type of experimental procedures we perform. And if we want to deny settings independence in this case, well, what makes us stop there? Perhaps we should abandon this assumption and we should abandon the enterprise of doing science in general. Okay, so that is settings independence. Those are the reasons why we believe that it is a reasonable assumption. And what are the problems that we might encounter with superdeterministic theory? I will now present our model, and we start by let me start by pointing out the trick that we are going to use. Okay, we're going to turn standard pilot wave theory. If I am not going to give the details of this theory, but during the questions, perhaps sometime it will be come back again. But we're going to turn this standard pilot wave theory into an equivalent but fully local model, and we're going to do a trick to do so. Okay, and it will be useful to have a name for this trick. I'm going to call it a Leibniz move. I'm not going to explain why, but the idea is to put in each physical space point in space the information regarding all the other points in the universe. Okay, and it should be clear that by doing that, it is possible to transform the dynamics of the model we are constructing in something that is local. The idea would be that each point has the information to do whatever it does without the presence of any other particle. Okay, so in standard pilot wave theory, we have two equations of dynamical equations. The first one is just the Schrödinger equation, and we have also the guiding equation that gives you the dynamics of the hidden variables that the theory proposes, which are just particles and their positions. Okay. we are going to use this Leibniz move, and in this, what we are going to do is to suppose that at each point in space there is an internal, there is a set of internal degrees of freedom, which are going to be a wave function field and a position field for each point. Okay, and we doing so, it is possible to obtain a dynamics that is fully analogous to the previous two equations. But we are now dealing with wave function fields and the position fields. Okay, and two comments regarding this move. The first one is the internal degrees of freedom at each point. They behave as an n-particle pilot wave system. So the idea would be that for each point in physical space, we now have an n-particle typical pilot wave system. And the second would be that the second observation would be that the theory only contains local bubbles, in the sense that it is not describing some interaction between whatever is happening in these points. The dynamics is completely described by what is happening at each one of these points, and therefore it's completely local. To connect this, the model with whatever we find in physical space, we specify a mass density. This allows us to say that a particular point in physical space is populated by matter only if the particles in the internal degrees of freedom of such point in physical space have a particle being occupied. So the idea would be, imagine that you have a point in physical space, there is the internal degrees of freedom, and if those internal degrees of freedom there is a particle that is at the same point that this point, or that this physical point is, then we find matter there. Okay. Okay. Crucial observations. For generic conditions, the model is we don't have much. Okay. We don't have violations of the Bell's inequalities, and we don't even have predictions of the predictions of quantum mechanics. Okay. But it is easy to see that under very particular initial conditions, that is, if the wave function field and the position field are the same for each physical point in space, then we have three clear consequences. The first one is that the points become suddenly coordinated, and we have a dynamics that it seems like it is describing some universe where things interact causally, but in fact, we just have points that are being coordinated. Second, we are able to recover all the predictions of the standard pilot wave theory. And three, where we have the violations of Bell's inequalities. 2 and 3 are related, since in pilot wave theory we have violations of Bell's inequalities. Okay, I'm not going to go into the details of this, but the question becomes, well, how can we achieve such an homogeneity condition? And in the paper we discuss 3 ways of doing it. The first one is by putting it by hand. The second is by imposing it as some type of law-like constraint, and the third one is by doing so dynamically. Perhaps during the questions we can talk a little bit about this. But okay, regarding the problems that superdeterministic theories seem to have, what can we say about our model? Well, I think that it is interesting to note that our model shows that it is possible to create a superdeterministic model that doesn't have the kind of problems that people feared. As it should be obvious, the conditions required to have a workable model are not as complicated as people thought they would be. The second point is that well, it has as much explanatory power as the standard pilot wave theory has. And the third is that the model shows that explains why settings independence is violated for Bell-type experiments, but it doesn't say that settings independence should be violated in other types of experiments in science. So there is no threat to experimental science. There are some problems with the model. The model is really ugly. We are not trying to argue that this is a good way to do physics in the world. We are just showing that it is possible to construct this model, and that it is a good place to continue having the discussion regarding whether or not something like superdeterminism is a reasonable possibility. In more detail, the model seems to require an absolute rest frame. Second, there seems to be a disconnect in the model between what we can call the ontology of what is really happening according to the theory and what we can have contact with. So the theory postulates these internal degrees of freedom for each point in physical space, yet we cannot go and see those internal degrees of freedom. In fact, the theory says that we cannot do that. Okay, we because of the mass density, it explicitly says when can we note something about all of these internal degrees of freedom, and it's under very particular conditions. Lastly, there is an obvious massive enlargement of the ontology in this model. Okay, let me finish with a list of contributions of that this work has done, and in particular that can be seen as consequences of constructing this model. So we have presented a model that is completely local, and it is able to reproduce the predictions of quantum mechanics. It does so without being too complicated, without losing explanatory power, and without making all experimental science obsolete. So the problems with this model were not the ones that many people feared. At least there are not these three problems. So as a proof of concept, it shows that it is possible to construct a superdeterministic theory in a way that keeps the physical details of what is happening. And finally, the model does all of this by very cumbersome methods, and doesn't seem to be to offer any advantage over other alternatives that are non-local. That's it.
Okay, thanks, Carlos. Thanks for this very nice talk. We are almost on time, so if someone has a very short question, you can pose it now. Otherwise, I invite Elias to start sharing screen. But if someone has a question for Carlos, please go on. I had, of course, questions, but I think we are quite on time. But my question was something like, we can, of course, speak later or by email or something like that, but you claim that the world is non-local, right? But then how can you have in a non-local world device measurements independence? For example, you will claim that in Bell inequalities, you don't have measurements independence or something like that because it is non-local. And then in your definition of superdeterminism, I don't understand, because if you want superdeterminism or if you want to avoid it, because when you pose a model like in Leibniz, everything is super, there is no, in Leibniz metaphysics, there is no measurements independence, because the monads, every monad knows what to do and knows what the rest of the monads are doing. So everything is super determined by the most perfect world chosen by God. So it's not clear for me what you, at least the conceptual definitions, right? What do you want to do?
You are completely right in the sense that if you believe in something like the universe of Leibniz's monads, or the kind of universe we're describing with this model, yes, that's a way to deny settings independence. And yes, that is a way to keep locality. But I think that most people would agree that that's a price too high to pay.
I see.